Okay, guys, so we have two more cases of examples to go through that are a little bit more sophisticated. But if we follow the same guidance that we took in the last examples, which is to draw the picture and determine the representative volume of cylinders and then add them up, it's not so bad. So we're going to consider two cases. The first, where we have to use washers, that is, where we're rotating a region that does not touch the x-axis around the x-axis. And another example where we're going to rotate around an axis that is not the x-axis. So the first example we'll look at is the case where we have, say, we're going to rotate the region bounded by y equals x squared and y equals x about the x-axis. Find the volume of the surface. Of course, step one in these problems, like usual, is going to be to draw a picture. So the picture that we're going to draw this time is going to look like this. So we know that we're dealing with the curves y equals x squared, which looks like this, and y equals x, which looks like this. And these curves intersect each other at 1, 1, and 0, 0. And what we're going to do is we're going to take the region between them, and we're going to rotate it this way, about the x-axis. So that's going to give us a slightly different looking shape than we've seen before. So if we look again at what this is going to look like, so you have one piece that looks like this and one piece that looks like this, and if you rotate it around the x-axis, what's going to happen is you're going to get kind of a cone on the outside, but then if you can imagine, it's almost like a funnel where there's a surface on the inside that curves in down towards a point at the bottom. This is hard to draw to give it dimensionality at 3 degrees, but you can imagine that it sort of curves in the way that, because the inside is determined by the parabola. So now, how are we going to figure out what the volume of this shape is, this trumpet bell? So we could look at a formula, or we could try to draw what a representative cylinder would look like, or a representative slice this time. The first thing is to notice that what's happening is we have the rectangle here on that region, and when that rectangle gets rotated around the axis, what it turns into is something that looks like a washer. So this is an example of what's called the washer method. And it's because the shapes that you get out are a big cylinder with a smaller cylinder that's been subtracted out of the middle. So what does that look like after you rotate it? Well, you're going to get the outside curve, which was determined by y equals x. And the inside curve right here determines the inside of the rectangle. That's going to be what gives you the inside of the washer. So the idea here is that the volume of this solid is equal to the big washer minus the hole that's been punched out. So really we can think of this as the volume of a big cylinder minus the volume of a little cylinder. And then the thing that we get when we do that is exactly what the representative pieces of this sort of horn shape over here turn into. If you can see what I'm talking about. Okay, so the volumes of each of those pieces we can solve exactly the same way we did before. The representative volume of the blue piece is going to be equal to, well, its width is delta x, and its radius, its distance is going to be the distance from the axis of rotation out to the blue edge here. So what is that going to be? Well, you can look up here in this picture and see the radius is the distance from the x-axis up to the curve y equals x. So the outside radius, or the radius of the big cylinder, is going to be r is equal to x. Because this point on that curve is the same as this point right here. For the red curve, well, again, I know that it's delta x wide, But now it's going to be the little radius. So since we're spinning around this axis right here, this little radius right here, this is the distance from the x-axis to the lower curve, which is x squared. So the radius in this problem, which I'll call little r for small radius, is equal to x squared, which gives me two different expressions for volumes, one for each of the cylinders. The representative example of the big cylinder is equal to pi big R squared delta x. And the representative volume for the smaller cylinder is V small is equal to pi little r squared delta x. And if you want the volume of the cylinder with the hole punched out of it, that is, if you want the volume of this thing, where after we've subtracted the red cylinder from the blue one, then you just subtract those two formulas. So the volume of the washer is equal to the volume of the big cylinder minus the volume of the small cylinder. Well, that's just pi times x squared dx minus pi times x dx. And I'm supposed to square both of these because it's capital R squared and little r squared. Again, remember, all we've done here is pi capital R squared delta x minus pi little r squared delta x. And the delta x's are really the heights. Pi r squared h minus pi r squared h. So that's the formula for a washer generically. Is in fact, if you look in the book, what you're going to see is something that looks like this. Pi times capital R squared minus little r squared h. So the volume of washer is the outside radius squared minus the inside radius squared times pi times the height. But really all you're doing is exactly what we did right here, where you take the washer and you think of it as a big cylinder minus a little one. Okay, so now with all of that, let's get back to our problem. So again, remember the idea was that we were going to try to figure out what is going on here. And taking that shape and spinning it around this axis. We know that for our washer, we think of it as a big cylinder which has volume pi x squared dx, or delta x. And for the little cylinder, we think of it as pi x squared delta x. Which means I actually made a mistake here because the volume of the big washer is x. So this should have been an x, and this should be an x squared squared. Okay. Okay, so the volume of the washer, that is the volume of a representative washer in our shape, is going to be those two subtracted. So the volume of a washer is going to be equal to pi x squared minus pi x to the fourth dx, or delta x. Now, I want to take each one of those washers. Remember, what's going on here is that we have this shape, this sort of hollow cone shape, and we're slicing it up into these kind of washery looking shapes on the inside. So I want to add up all of those washers from beginning to end. Well, the first washer is located at x equals 0, and then we cut washers until we get to x equals 1. So you can imagine that we're chopping this thing up into washers like this, and each one of them is located at some value between x is equal to 0 and x is equal to 1. So to sum up all the washers, we just do the integral from 0 to 1 of pi x squared minus pi x to the fourth dx. At this point, all we have to do is compute the integral. That's straightforward. We get pi over 3 x to the third minus pi over 5 x to the fifth, evaluated from 0 to 1, which is just pi over 3 minus pi over 5. And for me, you don't need to simplify expressions like that. This is algebraically sufficient. I mean, I'm going to trust that you can handle 8th or 9th grade algebra. So whether it's on a quiz or an exam or something else, high school level or prior, elementary school arithmetic, simplifying fractions of numbers, just leave. It's easier for me to read the answer if you don't, and you're less prone to making mistakes that way. Okay, so we have one more example to do. In this problem, what we did was where we've got two different curves, but we're still rotating around the x-axis. But you notice that gave us two different radii to deal with. So we're going to get the same kind of idea, the same sort of expression where we always get washers when we take a region and we rotate it around an axis that is not the x-axis. So that's the final example that we'll go through together here. So this will be example 4. So I'm going to set this up with the same sort of setup that we had last time. So find the volume of the surface obtained by rotating the region R about the line y is equal to -3, where the region is the same region from the previous problem. That is, it's the region here between the curves y equals x and y equals x squared, where the x values range from 0 to 1. But now, instead of rotating it around the x-axis, we're actually going to rotate it around a line down here instead. So we're going to take this entire shape, and you can imagine that instead of rotating around here, this is the axis of rotation. And what that means is every single slice in this object is going to be a washer. This is sort of like a flower-like shape, for lack of a better term. I'll try to draw it on the next page. Okay, so what is the actual region we're working with? Well, we know we've got y equals x right here. And we have y equals x squared down here. And the region that we're trying to rotate is the region between it. Now, where are we rotating it? We're rotating it not around the x-axis, but a line that's down here at y equals -3. So there's a line down here at y is equal to -3. And we're going to take that shape and we're going to rotate it like this, not up here around this line, but down here around the axis of rotation, y is equal to -3. And so you can imagine that if you sliced through this object, that there would be another section of it down here that looked like this. And that there would be these circles that determined the sort of bottom and top of this shape. So it's hollow, kind of like a piece of a cone where you've sliced the end off. Or if you took an ice cream cone and bit the end off, right? This would be the kind of shape you get, except it has this curved interior, so there's definitely a volume here to be computed. Well, every slice I take of this thing this time is going to be a washer. And the only question that we've got is, well, what's the radius going to be of the cylinders that this is going to decompose into? Well, let's take a look. So suppose that you just cut through the object like this, and you try to see what the cross-section looks like. So you just take your knife and you slice through. What do you get out? Well, you're going to get a washer that looks like this. On the outside curve is going to be this sort of blue guy up here, down here. And the inside curve is going to be this sort of red piece that looks like this. And the question is, well, what's the radius of these two pieces? I can't compute the volume unless I know the radius, like how far it took me to get from here to here, right? If I don't know the radius, I can't decompose this thing into two cylinders and subtract. So this time I have a non-simple radius that I have to compute because I'm not rotating around 0, right? I'm rotating around a number. And the way that I compute a distance is I subtract the two numbers that I'm trying to see how far apart they are. So what is the distance from the axis of rotation up to the top of the curve? Well, it's not y equals x this time, because now the distance is from y equals x to the middle line, which is y equals -3. So you actually have to subtract to get the radius. So the capital R, the outside radius this time, so this distance right here, this outside radius, is capital R is equal to whatever you got to up here at the top, which is x minus the axis of rotation, because you have to go all the way from here down to here. -3. So the radius this time is actually x plus 3. That's the radius of the big cylinder. What's the radius of the little cylinder? Well, again, you have to get from -3 up to this inside curve right here. So this radius from here to here, little r, is going to be x squared minus -3, which is the same as little r is equal to x squared plus 3. So just because they both have plus 3's, you expect that because they're both being rotated around the same axis. You can't just throw them away algebraically, because the formula for a cylinder has an r squared in it. So what is the volume of this shape, of this representative washer here? So again, to reiterate, this is the line y is equal to -3. Up here, I had a curve that looked like this, which was y equals x. And down here, I had a curve like this, which was y is equal to x squared. And this distance was r is equal to x squared minus -3, which is r squared plus 3. And this distance is capital R is equal to x plus 3. That is x minus -3. So when I build my washer, the big part of the washer, that is the part that touches this curve right here on top, is going to look like this. So I've got this big cylinder, and its volume is going to be pi times x plus 3 squared delta x. Because, of course, like usual, these things are delta x wide. And the little cylinder is going to be given by, well, it's also delta x wide, because it's just a hole punched out of the blue cylinder. And its volume is going to be given by v is equal to pi times x squared plus 3 squared delta x. And so this is not a computation where the 3's are going to cancel out. It's all going to have to be computed. Okay, so that means that the volume of the representative washer, so the washer volume, so remember that the volume we're trying to compute is the volume of the washer, which is what you get when you take the blue cylinder and punch the red cylinder out of the middle, which is the same thing that shows up when you take a shape like this and rotate it around this axis, because it's got this big hollow space in the middle. So when you're approximating volumes of objects that have hollow spaces in the middle, washers are the thing that occur. So the washer volume is going to be pi times x plus 3 squared plus pi times x squared plus 3 squared, I should say minus, all of that times delta x. And that's going to give us a little bit more of a nitpicky integral that we have to work through, because the integral that we're going to get in this case is going to be the integral from 0 to 1 of pi times x plus 3 squared minus pi times x squared plus 3 squared dx. And to solve that integral, we're going to have to multiply out and apply the power rule. Okay, so for the last step, let's just do the integral. So we've got the integral from 0 to 1 of pi times x plus 3 squared minus pi times x squared plus 3 squared dx. Now, I'm going to continue to remind you that when you look at a formula like this, you should be able to identify all the pieces, okay? So this thing right here is pi times the outside radius squared times the height of a cylinder. And this part of the formula says, well, okay, now subtract off an inside radius squared times pi. So that's a small circle times dx, which makes it a cylinder. So this is a volume minus a volume that we're looking at. And I want you to be able to recognize that it's a volume minus a volume. Okay, now I can't do anything until things are FOILed out. So this is going to be the integral from 0 to 1. Since both terms have a pi, we can pull the pi out. X plus 3 squared is x squared plus 6x plus 9. And then we're going to subtract off x to the 4th minus, or plus 6x squared plus 9. And all of that has a dx on the outside. Simplifying terms gets us the integral from 0 to 1 of negative x to the 4th. And then that looks like the There's a minus 6x squared, there's a plus 6x, and then 9 minus 9 disappears, dx. So this is what I mean about being careful with your algebraic cancellation, okay? All right, so to finish this up, all right, so integrate the inside using the power rule. Remember that the power rule is that the integral of x to the n dx is x to the n plus 1 over n plus 1 plus c as long as n is not equal to -1. So this is minus 1/5 x to the 5th minus 6/3 x to the 3rd minus 6/2 x to the 2nd, evaluated from 0 to 1. If you punch through with the 1, you'll get pi times minus 1/5 minus 2 minus 3 this is supposed to be positive. Careful with your signs. Integration is one of those things where it's really easy to lose a sign. I knew that I was wrong because the number I'd come up with was a negative number, and there are no such things as negative volumes. So this all turns into something like 4/5, I believe. And then the pi from the front is left over. Okay, so if there's any questions about how that integration was performed, please let me know. And I will provide some more written examples of all of these things as we go on through the week. So thank you very much.